With that, I'd like to welcome everybody to our SymCorrel2021 flash session. This is a little flash session where everybody will have 2 minutes to just quickly present 1 or 2 slides about their contributing talk. Sorry, someone say something? No. About their contributing talk, which you will find if you go into the Meet Now, our meeting platform, and you click over to the contributed talk link, you can see them all in a list, and you can just click on them, and then we'll basically you will see like a YouTube video, which is just kind of imposed into, it will show up in your Meet Now kind of window, and you can go through all the talks and listen to them there. All right, with that, I think we can get started. This is the order in which we will see our presenters today. So first, we would like to welcome Chian. I hope I'm pronouncing that correctly. Please correct me if I'm not, from Peking University. I think, are you here, Xi?
Yes, I'm here. Thank you very much. It's correct. So my name is Chian. Hello, everyone. I'm from Peking University, and it is a great pleasure to be here. And my talk is about electron correlations in titanium oxide systems. And in this talk, I will present our recent studies of the systems using ab initio calculations. And in the last few years, we have been very interested in titanium oxide systems, which have shown interesting physical and chemical properties. I think it's known to many people, as well as some promises for industry applications. So especially when titanium oxide systems are used as a prototypical systems for understanding electron correlations in transition metal oxide systems. So we have been very keen at pushing the limit of the accuracy of ab initio calculations by employing different state-of-the-art approaches, such as FuCi QMC, coupled cluster, etc., and to combine these approaches with methods such as some embedding techniques suitable for treating solid systems. And in this talk, I will discuss several different systems from TiO molecular to defects in titanium dioxide. For TiO, a relatively small system, we are able to achieve FuCi QMC benchmark level calculations, and for oxygen vacancy in titanium dioxide, we have done some CCSD bracket T level calculations, and also compare these results with DFT calculations. And for surfaces, we also find some very interesting behavior between polarons in the substrate interacting with water. And through these studies of these systems, I hope that we can provide some insights to the general features of electron correlations in titanium oxide systems. And specifically, you will see that both the moleculars and the TiO2 systems show strong and similar sort of dynamic correlation features. So I hope these insights could also help us to design better methods in the future to characterize these systems. That is basically the main message of my talk. And thank you for attention, and welcome to my talk. Thank you very much.
All right, thank you, Xi. Great talk. All right, so moving on, next up is Branislav Nikolic. I hope I'm pronouncing that correctly as well. Are you here?
Yeah, thanks. It's excellent pronunciation. Can you hear me? Yeah, so this talk is about non-equilibrium quantum antibody systems. It's not quantum chemistry, but it is directly related to the session on the density matrix renormalization group, which is this evening. So basically, it is transgressing between 2 different fields. It is spintronics. Most of the time in spintronics, people use either something which is counterpart of molecular dynamics, which is called classical micromagnetics, which means they treat spins as classical sticks rotating, or they use quantum classical methods, same as in chemical physics, and I have developed some of them, and I'm moving them back and forth between physics and spintronics. But in this talk, I'm going to discuss the need to actually put real quantum any-body physics into the game, which has been overlooked in the past 25 years. So spintronics is an interesting field because you can combine a very fundamental interactions between many electrons and localized spins together with something real and practical, such as devices. So the basic device is this one on the top, which is called spin wall or magnetic tunnel junction. It has two magnetizations. You inject electrons into it, you make the two magnets non-collinear, and then what will happen is that these flowing red electron spins are going to initiate magnetization dynamics. And that magnetization dynamics can be very complicated and very useful. So if you succeed flipping magnetization from up to down, you get a memory device, which is this red dashed circle. And these memories are already on the market. You can purchase them. They're kind of emerging. If you want to risk, you could put all of your retirement money into the company with the ticker symbol MRAM, and one day maybe they will be big and you'll become rich. So in any case, this is a #1 topic in all of the spintronics, the so-called spin torque. And one interesting thing is that since 1996, when this was brought to attention of technology experimental communities by theorists, it's a pure theory predicted in 1996, and there was a Buckley Prize for it. People have been using since that time exclusively formalism, which is similar to quantum classical formalism in chemical physics, where localized spins, such as the black one on the top, receiving the torque, are treated as classical vectors, and electrons, of course, must be treated quantum mechanically, which is why in this equation in the yellow box, I'm cross product doing trace of the non-equilibrium spin density matrix and Pauli matrix with this classical vector. And this has been perfectly sufficient until, let's say, 3 years ago, and that's the next and last slide. And so what happened 3 years ago, somebody said, let's cool this device to 1 Kelvin. And once you cool it to 1 Kelvin, everything gets frozen, and it looks like that all of these effects should be gone because everything is parallel and the cross products are 0, but experiment has observed a non-trivial effect. And the explanation for this was quite hand-waving in the original experimental paper. Even though the paper has a lot of great insights, they thought it's some kind of quantum fluctuations that are tilting the things to become non-collinear because that's the major requirement. But it turns out that even if everything is collinear, which is incoming electronic spins and these local spins, you can still initiate this non-equilibrium dynamics. And the dynamics is actually completely non-classical. So this is one example where you would have to give up on your classical formalism and start doing full quantum any-body physics. And the counterpart of this in chemical physics would be your molecular dynamics becomes invalid. And you have to switch to completely to quantum any-body dynamics. And why would the molecular dynamics become inapplicable in chemical physics problems? Well, it has to do with entanglement, same thing here. So what happens at low temperatures is that you start entangling spins, and these vectors that Lambda and Lifshitz considered in 1935 to be classical objects of fixed length just rotating start changing length. And in particular, I don't think you can maybe run this. There's 2 movies actually that are something for general audience produced by time-dependent density normalization group. So in these movies, you can probably not run them, but you can see them in the talk. I'm running them for the audience. What you would see is that instead of seeing a standard vector which is rotating, which would be the counterpart of molecules moving along Newton's second law trajectories when you're doing molecular dynamics, you basically see these vectors just changing in length along the z-axis. And I don't know what would be the counterpart of that kind of motion. Oh, you can run the movies, okay. So like you inject the electronic pulse, which can be done with TDD-MRG, and they hit these spins. The spins are all collinear to each other, but anti-parallel. And you see that these localized spins are now flipping, but they never tilt away from the z-axis direction. Instead, they're just changing length. And of course, this is a completely non-classical effect, and it's purely due to many-body entanglement, non-equilibrium one between the flowing electron spins and localized spins. And if one actually calculates, as is this box on the bottom, so-called mutual information between the first and last of these spins, you would see actually long-range entanglement to infinite order. And the second movie shows what would happen if you do the same process of trying to inject a current pulse, which is polarized. You could try to move the mouse over the second movie. If you try to inject the current pulse into antiferromagnetic multi-insulator, for example, nickel oxide, or one of these, many of these antiferromagnetic insulators are actually highly correlated systems for which DFT, GW, everything is broken. You must shift to either these fully many-body methods or DMFT and things like that. So in this case, we are using DMRG. And if you inject current pulse, you would see a very interesting transmutation of this antiferromagnetic multi-insulator into some kind of inhomogeneously ordered ferromagnet, because it is a non-equilibrium phase transition driven by current injection. And okay, this is basically in a nutshell something completely new, because for 26 years people have thought that you would never see these effects unless the flowing spins and local spins, the red and blue guys on the very bottom right, are non-collinear. But now, according to this quantum antibody picture, it looks like that you can observe this dynamics driven by current if you make incoming spins anti-parallel to local spins. And one could think, like, most of the spintronics is focused on room temperature, what would be this useful for? But it's all about quantum computing, because you can think of these red guys in the bottom right as being spin qubits. So this is one way to manipulate spin qubits and collect all of the stories I try to sell you to quantum computing. Thanks a lot.
All right, thank you. All right, next up we have Ritesh Pant, I think. So that hopefully that's correct as well.
Hello, I'm audible, right? Hello.
Hello, yeah, we can hear you.
Yeah, okay. Yeah, thanks for the introduction. So I'm Ritesh Pant, and today I will talk about this excitation transport in molecular aggregates with thermal motion. What you see here on your screen now is the thermal vibrations of these molecular aggregates. So if you can play this movie, the first one, where these molecules are, so this FMO molecular aggregate, can you get it? So, yeah, anyway, it's fine. So these molecules are vibrating, and these are placed inside the cage of protein. So these yellow color strips and these purple color strips, this is the cage of protein. And now suppose one shines sunlight on this molecular aggregate. So that sunlight will be then absorbed by a molecule that then excites the molecule from the electronic ground state to electronic excited state, as you see in this animation. So you see that this excitation energy then jumps from one molecule to next molecule, unless it ultimately reaches the reaction center, and where some charge separation will take place, and that will create a potential difference, and that will be the nicer way to store the energy, right? So this idea of light harvesting by molecular aggregate has been used in making these dye-sensitized solar cells, and where we use these molecular aggregates to absorb the sunlight and to funnel the sunlight to the semiconductor in a similar way they are doing for plants. But there is a problem, like if you can see this, you can't play this movie, but there are thermal vibrations present in this aggregate, right? And so thermal vibration as well as the environment in which these molecular aggregates are. So this results in the trapping of excitation on a finite number of modes. So that will that is called means these vibrations or this environment will localize the excitation energy on a finite number of monomers or molecules, and that will reduce the efficiency of excitation transport. So this is one of the challenges in this excitation transport, right? So in this direction, then we study how the motion of molecules affect the this excitation energy transport. So for that, as you see here in these two animations, we include two types. We study two types of motion. One is torsional motion, where the molecules can wiggle around the equilibrium position. These blue colored these are the molecules, and these red color arrows are the direction of transition. So for these two types of motion, we study how this exciton trapping problem can be resolved, right? For that, we use this Stellate surface hopping algorithm, where the dynamics of molecule is treated using classical equation of motion, and the transport of excitation energy among the molecules, that is treated using Schrodinger equation of motion. So ultimately, what we do is that we calculate this efficiency of excitation transport. The expression that you see here is E tau, that is calculated as the probability for the excitation to reach to the output side. So we take some input side, that means initially the molecule is excited, and then that excitation then jumps to the output side. And neta here you see is the relative efficiency. So we compare two efficiencies when the molecules are moving and when the molecules are static. And what we found in this paper is that there is this significant increase in the efficiency of transport when motion is present there. So these results are all there in the paper. So if you are interested, you can have a look at the paper. So that indicates that the motion of molecule can help us in improving the transport efficiency and avoiding that localization or the excitant trapping that is there because of the environment. So for more details, you can have a look at the paper. And thank you so much for your attention.
All right, thank you so much, Ritesh. Next up, we have Onur Pusuluk. I hope I definitely did not pronounce that one correct. I apologize for that. Are you here, Onur?
Yes, can you hear me?
Yes, we can hear you. I'm moving on to your slide. There we go.
Thank you very much for the organization. The principle of quantum superposition has been one of the most important theoretical and computational tools for understanding the nature of chemical bonds. And the approximation we use to describe chemical reality, such as hybridization, resonance, or molecular orbitals, are in fact superpositions of atomic orbitals. Similarly, superpositions of different slater determinants form the basic assumption behind the fastest and most accurate quantum chemistry methods we have developed. And in this talk, we focused on the next step in building our understanding of chemical phenomena using the tools of modern quantum information science. One of the recent developments in this field is the discovery that the superpositions shared in composite systems, namely the quantum correlations, which are known as entanglements and more generally discord, can be used as a resource in quantum technologies. For example, even in the environments entanglement vanishes, quantum discord can survive, and it may lead to spontaneous heat flow from a cold body to a hot one, or prevent heat from flowing between two systems at different temperatures, or actuate a heat exchange in the absence of a temperature difference. It means that these resources are real as much as energy. And can you change the slide? By developing a methodology compatible with all conventional quantum chemistry algorithms, we investigate orbital correlations in the presence of superselection rules. We introduced the notion of orbital discord, which enables us to present the first proper decomposition of the total orbital correlations into its classical and quantum parts. Here, I and C stand for the total and classical orbital correlations, respectively, and both of them are quantified by different generalization of different quantum generalization of mutual information. And D denotes the quantum orbital correlations quantified by orbital discord. And finally, E represents the orbital entanglement. Remarkably, we demonstrate that quantum orbital correlations can be stronger than classical orbital correlations, though not often. Let's compare the orbital pairs 3 and 5 or 4 and 5 in the upper illustration. Our results illustrated in the middle reveal that quantum orbital correlations can survive even in the absence of orbital entanglement. And this depends on the symmetries of the constituent orbitals. And as shown in the lower illustration, we have also examined whether the symmetries of the constituent orbitals make a difference in terms of correlations. And besides this, when the orbital density matrices are treated as qubit states, we have shown that orbital entanglement would be underestimated. I hope you will enjoy the talk, and thank you very much once again.
All right, thank you, Onur. Next up, we have Sebastian Mantilla Serrano.
Yes. Thanks for let me share this research project. And also really well pronounced, actually. The Mantilla sometimes is difficult for some people to pronounce it. So I really appreciate it. This is just a small part of my research that I'm doing as a part of my PhD with Inti Zodeman, my thesis advisor at the Max Planck Institute of Complex Systems. And this is just a method that we are designing to address problems in which we have electrons or many fermion systems in which there are interaction, long-range interactions among them. So yeah, thanks. So the system that we're addressing is one of the simplest one. It is just nodal semi-metal, so you know that you have two bands, and then we are studying how the electrons excite. So how can we generate the excited states of this system? Temperature 0 at the moment. And then what we found is that we can use an isospin picture. So, you know, trying to rewrite the same operators in different ways, like for instance, going from fermion to spin and from spin to hardcore bosons. And then we can find really fine quadratic bosonic Hamiltonians that not only let us solve the problem in an easier way, because at the end it's just diagonalizing a simpler Hamiltonian, but also it can give us some physical insight of what's going on inside the system. Like for instance, the production of excitons inside it and how these excitons interact to each other. Like for instance, my model in these interactions has hoppings or pairings among them. So there is still the possibility that they may condense, but not in the specific case that I'm showing in the presentation. So then the presentation consists on just a simple monolayer graphene with the Coulomb repulsions. And then what we found is that we can reproduce, for instance, the corrections on the dispersion relation, on the way in which the band is corrected because of the interactions, and also the optical conductivity. So with the optical conductivity, we found that we can reproduce not only the first order perturbation theory results, but also we can go to further in coupling. So we can go to strong coupling and still getting a result that may be consistent with the experiment. So this is what's going on in my presentation. I hope that you can enjoy it. I forgot writing the reference of my paper here, but you can also find it in the video. Thanks a lot for your attention, and I'm waiting for your questions in case you are interested. Thank you.
All right, thank you, Sebastian. Next up, we have Saurabh Singh. Is Saurabh Singh here? Let's see. That doesn't look like it. So I guess we'll skip him for now and move on to Alexander Schuckert.
Yes, hi, can you hear me?
We can hear you. Let me move on. This is yours, correct?
Yes.
Okay.
Okay. Yeah. So in my talk, you'll find out what trapped ion quantum simulators have to do with bees. And the common denominator between the two is the transport process, which happens. So trapped ions can be described with a long-range interacting spin system. And we developed a non-equilibrium quantum field theory to describe the non-equilibrium dynamics in such spin systems. So we use essentially a kind of non-equilibrium GW approximation, which you might be more familiar with. And what we show is that the transport is essentially the same as the one that bees do, namely a Levy-Flight superdiffusive transport process. And very recently, we also teamed up with the group of Rainer Blatt in Innsbruck to show that this indeed also happens in the experiment. And you can see the two papers in which we published the results up there. And I'm very happy if you come to my talk. And if you have any questions, please feel free to contact me via email or any other way. Thank you.
All right, thank you, Alexander. Now next up we have Scott. Scott Smart.
Hi, thank you. I guess, yeah. So my name is Scott Smart. I'm a PhD student with David Masiotti at the University of Chicago. And so my talk is just on resolving correlated isomers of benzene on a quantum computer with an error mitigated quantum contracted eigenvalue solver. And so it's a long title, but really I just hope to convey kind of three simple points in the talk. And the first is just, which probably most of us are familiar with, but why are we interested in quantum computing for simulating, strongly correlated molecular systems? What potential advantages are there? What problems are there currently? And what could we maybe expect? And then second, what is a quantum contracted eigenvalue solver? And so you can see in the bottom left, there's the anti-Hermitian contracted Schrodinger equation, which is the anti-Hermitian part of the contracted Schrodinger equation. But we utilize this contracted eigenvalue equation to develop a polynomial scaling quantum algorithm. And then actually, the last thing I'd like to just leave you with is maybe what are some ways that we can leverage the sort of, they call it NISQI or noisy intermediate scale quantum devices that are very error prone, have a wide kind of variety of performance, but generally, how can we get beyond just doing 1 or 2 qubit simulations? And so we're able to target the correlated isomers of benzene, which, for instance, the para-benzene molecule has some biradical character, and we're actually able to resolve these sort of relative energetics using the IBM quantum devices. And so I hope there's anyway, there's just a brief overview of the talk. Thank you all for your time.
Great, thank you, Scott. And then let's move on to Gunnar Möller.
Yes, hello. There's my slide. So the first one is just to say what the title is. So it talks about an interaction-driven quantum Hall plateau transition, which takes us between an integer and fractional Chian insulator in the Harper-Hofstadter model. This is work I've done with my student Leon and Frank Pollmann, I should say, here in Munich, as the conference is officially happening over there, but of course nobody is actually there. So let's move on to the next slide and I'll tell you what it's actually about. Okay, so the Hofstadter model has this very elaborate fractal spectrum that you might have seen before. And so here we're in some business of studying the many-body physics when we put particles into this lattice model with magnetic field. And as you can see, the spectrum has many gaps, which are these white areas between the black bands. In the center of the figure, I've shown you a little blow up of that. And so if you have fairly low density, what you can do is just fill some of the very lowest bands until you hit some gap, and that will give you a Chian insulating state. And that's true in the non-interacting limit of the system. But then if you turn on interactions, we know that the lowest lambda level, which is the ensemble of all the states that are below the red diagonal line on the upper left plot. So if the lowest lambda level supports fractional quantum Hall states at particular filling fractions, like the ones there are given by the Jane series of filling factors given by p over 2p plus or minus 1. And if you choose your numbers right, you can actually get one state of either type at the same density. And while the integer Chian insulator is requiring weak interactions, the fractional quantum Hall states, they require some finite repulsive interactions to be stabilized. So we look at the transition between these two regimes. And if you show me the next slide, what's quite surprising is that at least at this flux density there that we studied in detail, n phi equals 3/11, we find a direct transition between those two regimes. And it seems to have some critical properties. At least there's a fairly significant peak in the correlation length and entanglement entropy in our numerics for finite cylinders. And looking at the finite entanglement scaling of the entanglement entropy and the correlation length with the bond dimension of our MPS representation, we find a fairly nice linear scaling, and the coefficient out front, which informs us about the central charge of the equivalent critical theory, appears to be increasing with the system size of our finite size simulation. So that's very intriguing. And if you want to find out more about it, please go check out my talk. And there's also a preprint, which is a bit older, and the referees asked us to do more numerics, so that's what we've done, and new version is coming up shortly.
All right, thank you so much. All right, so now we move on to our last speaker, which is Paul Johnson.
Thank you very much. So I work in strong correlation, specifically, how do we solve the strong correlation? Sorry, come on. Okay, so how do we aim to solve strong correlation? How do we solve any problem in physics? We start from a system that we can solve exactly, very easily, and then expand perturbatively, couple cluster, whatever. So for weakly correlated systems, Hartree-Fock plus small corrections. We are proposing to solve strongly correlated systems in exactly the same way, using instead pairs of electrons rather than individual electrons. Other groups are doing similar things. So in particular, Gustavo is going to talk tomorrow, where they do AGP, which is identical pairs. We are using pairs from an exactly solvable model, in particular one that you can solve with an algebraic bit of Onstad's. So we can go to the next slide. The approach here has several advantages and disadvantages. In particular, the curves that I show in the talk are not perfect. That's because these results are old. They were our first numbers. If I were talking 2 weeks from today, I could show you some curves that are much, much better. And by how good are they? Well, perfect to 8 decimal places. Why not 9 decimal places? Because we've stopped the convergence criterion somewhere. Anyway, what we care about, variationally variationally feasible, mean field cost, 1 vector, no active spaces, 1 vector. You get a complete set of eigenvectors in which to develop your wave function, and everything is clean and understandable, very easy to compute. So that's just baseline what's important. In the near term, we have some difficulties, such as how do you find your initial guess for your optimum. It's a bit tricky to optimize. So brute force is fine in the near term, but eventually we should figure out how to optimize this correctly. And there's some hard work on paper to do. But all the machinery is there. It's more complicated than working with slated determinants, but it's no more difficult conceptually and only marginally more difficult numerically. So thank you very much.
Great, thank you. So just asking before we finish up, let's see if Saurabh Singh is here, or is he still absent? Doesn't seem like he's in the participants. So I think with that, I'd like to thank everybody for the great little overview, and I really urge you all to go into the meeting portal and really look at all the contributing talks. And if you found anything interesting, really watch all these great talks. And with that, I would like to thank you all for attending our little flash session.